Okay, so we were talking about surface integrals last time, and the idea was that we want to integrate over a surface instead of a curve. That's pretty much where we are. So we did this one where we integrated over the top little cap part of this sphere, and we were integrating a scalar function. So we were integrating f of xyz was xyz with respect to surface area. We use a double integral because it's a surface instead of a single integral if it was a curve. And then I said that there were a few applications that you could do, that you could find the mass of a surface, the center of mass using these formulas. And I believe that's where we left off. I did talk about the special case, and then we were going to start this. Okay, so it says, find this surface integral, so the double integral over the surface S of the function, the scalar function x, with respect to surface area, where S is shown below, and S is the entire surface. So we've got this cylinder that's been sliced. We've got this back cap, this red cap on the back of it. We've got this front blue cap, and then we have the actual cylinder surface itself, which appears to be green here. And so I've labeled the green, the red, and the blue here so we know what each of those surfaces are. So let's start with the red surface. The red surface is a plane, right? It's flat. It's x equals 0. It's the YZ plane. Then the cylinder is the green one, is y squared plus z squared is 1. So its cylinder goes down your x-axis, has a radius of 1. And then the blue is a plane again. It's the plane x equals 1 minus z. So what we need to do is come up with parametric representations for each of the three surfaces, all three. All right, so get my notes here. Let's start out with, well, which one do you want to start with? I don't care. The red one? The green one. Okay. What would be the green one then? Okay. That's right. It's a unit circle, so sine squared, cosine squared, and sine squared should give it, or not squared, cosine, right? Cosine u, sine u, something like that, with a radius of 1. Okay, I'm with you, but let's. Hey, welcome. I got your email. I just haven't gotten to it. I've been so overloaded with emails. All right. I guess it got to snow on the bridges and stuff. Yeah. So let's call the blue one out front. Why don't we call this one S1? The green one on the side here, why don't we call that S2? And then that cap on the back side, let's call that S3. And you said you wanted to find S2 first, right? So let me try S2 first. S2, I need to come up with parametric representation. So I need an RUV. And maybe I should go back because it has been a while and remind you of the formula we're trying to get here. We're trying to do a double integral over a surface of a scalar function with respect to surface area. We need to figure out what the function, the scalar function is, evaluated on the vector curve, or on the vector surface. And then we need to multiply that times the magnitude of the cross product of the partial derivatives, and then convert that into a double integral over D, where D is the domain of our UV. All right. I'm just trying to remind you what we're trying to do here. So I need my R of UV so I can find partials and all that stuff. Now, from what I gathered from what was recommended, because it is the cylinder, we do want to use cosine U, cosine V, cosine U, cosine U, sine U. That'll give us a radius 1. But remember which direction this cylinder opens. So which of these vector components do we want the cosine and the sine to be on? You go back to the picture. Here we go. X is free. So looking at this equation here, so you can make the y the cosine u, right? And then make the z the sine u. Fine with me. Cosine u, sine u. That should draw you a circle, right? This should draw you a unit circle and a fixed radius, right? And then now what we need to do is see how far back and forth on the x-axis we can go. So the x-coordinate, right? The x-coordinate of this is going to vary back and forth, right? Just imagine being on this cylinder, back and forth here, back and forth. So my x-coordinate is always between two values, right? What two values is it between? So what's the smallest x value it can be? This backside, which would be 0, and then it needs to come out to where? How far? Well, that's going to be dictated by that blue plane, isn't it? Which I've kind of cut off here. Doesn't that blue plane dictate how far out we come? So what we're going to do is we're going to let our x-coordinate be the v. Remember, we have two variables to play with. We're going to let our x-coordinate be v. We already know that u has to be between where and where? The u. 0, 2 pi, that'll draw our circles. But our v now needs to be stuck between where and where? 0 and 1 minus z, right? But z for us is what? Sine u. Got it? So 1 minus sine u. Okay, that's S2. Would you like to go ahead and get the surface integral on that right now? You want to do that? And then we can come back and we can do that. We got to do all the surfaces. So let's do this one here. Okay. Double integral over the surface S of, what was the function? X ds should be equal to the double integral over d of f of r of uv times the magnitude of the cross product of the partial derivatives of r dA. Right? That's what we want. And let's label this down here. See how I have S down here? Let's label that S2. Okay? Because we are just going over S2 right now. We'll have to come back and do S1 and S3. All right, so let's get some partials. Partial of r with respect to u is a vector. It is the vector, what is it with respect to u? Okay, so 0, negative cosine u, sine u, or negative sine u, cosine u. Cosine u. That okay? What's r, partial r with respect to v? 1, 0, 0. And now we have to take a cross product, don't we? So what is r partial r with respect to u crossed with partial r with respect to v. So this is a vector, isn't it? So let's see how quickly we can work this out. We want the I component. We do this determinant. We should get 0. To find j, we do the determinant. And we get negative cosine u, but then we subtract it, so it should be positive cosine u. And then to get j, cover up 0 cross negative and changes signs again, so sine u. Wow, that's going to be nice, isn't it? Because if we cross those, take the magnitude now, we get what? Bonus, if you have bonus, yeah, right here. It should just be what? Square root of cosine squared u plus sine squared u, which is 1. So we just get 1. So let's go ahead and rewrite that double integral up there. The double integral should be double integral of what is our function evaluated here. So what is our function that we're integrating? It's the x function, right? So all I want to do is plug in the x component of my vector surface, my surface vector. So isn't that just v? That's just v, isn't it? So this should just be v, and then times the magnitude of the cross product thing, which we found was 1, and then dA. So dA. Which now becomes, now let's talk about the domain of our vector surface. What was the domain we had? 0 to 2 pi, right? 0 to 2 pi for u, 0 to 1 minus sine u for v. So we go 0 to 2 pi and 0 to 1 minus sine u, and this is v, and then d what, d what? du dv? Does it matter? Hold on. We have to go dv first, then du. Because u is between two constants, right? U is between two constants? Okay. Go by that? Any questions? So there's your function evaluated at the x component of the surface, which was v. We got our 1 in there. We got our limits of integration. Let's go ahead and evaluate this, okay? Or should we use Mathematica to do it? You use Mathematica to do it? Okay. So we're going to go 0 to 2 pi. Then we're going to go 0 to 1 minus sine of, was it u, right? And then we're integrating v with respect to v, then u. When we get this, we get 3 pi over 2. So this should come out to be 3 pi over 2. All right, that's just one of the surfaces. So now let's do S, what do you want? S1 or S3? You want to do S3? S3 is going to be easy. Here's why. On S3, we are looking at, where is it? What are we looking at on S3? It's just the back side of that, right? It's just the back side of this. So check this out. I could go through the whole work of trying to come up with the parametric representation of this, right? Yes? Maybe we should at least start it. What would the parametric representation of that be? That red disk. What can you tell me about the x-coordinate? It's 0. And then what about the y-coordinate? We could say something like u sine v, and then u cosine v. Or, sorry, I was using cosine and sine. Cosine v, sine v. So remember, this is how we draw disks, right? We vary the radius, and then we vary the angle. So here, v would be between 0 and 2 pi. That would make sure I go all the way around, and then my u would go between where and where? 0 in the radius, which in this case was 1. Can't really see it there, but there it is. It was y squared plus z squared is 1. Okay, so, but here's the thing, though. Instead of me going through and finding the partials and doing all that, just check this part out. I'm supposed to do double integral over s, right, of the function of the function x ds, which is the double integral over d of the function evaluated at the vector surface, right? And then magnitude, all that stuff, right? Why can I stop now? Yeah, what is the function I'm evaluating on that surface? Well, it's the x-coordinate, right, or the x-component of my surface. The x-component of my surface is 0, which means I'm integrating 0, which is 0. So I don't have to do any work. So this is equal to double integral over d of 0 times the magnitude of all that dA, which is 0. So no work necessary there, right? Now, had this been y instead of x, well, then you would have had to do it, right? So we got lucky. How about S1 now? S1 is the blue one here. How are we going to get that blue one? Well, the blue one is a disk again, right? I mean, when we look at it this way, it's just a disk. The only difference is that the z-coordinate, sorry, not the z-coordinate, the x-coordinate is not fixed at 0, right? It's just like this one, except that this is not fixed at 0. That changes, right? And that depends on exactly where you are. So how can I determine what that x-coordinate is? Well, it's just this. It's 1 minus z. And our z-coordinate is what? U sine v. Y'all okay with that or no? No? Yeah? No? You're not? Not? Okay, well, good. Okay, so I think everyone was okay with the fact that that red disk was x component 0. That was what made it flat. And then letting, what was it, u cosine v, u sine v would draw this, right? So imagine the y and the z coordinates all living on this right here are identical to the y and z coordinates that live on this one, right? Looking at it from this. They look exactly the same. So the y and z coordinates are identical. What's different is how far in and out, or on the x-axis, how far you move. So if I have a y and z, let's say in this first quadrant, let's say right here. The only difference between that one and the red one is that I have to bring that out somewhere, don't I? How far I bring it out is dictated by that equation. The x-coordinate must be 1 minus the z-coordinate. So whatever your z-coordinate is, whatever your height is here, that's how far you come out. 1 minus that is how far you come out this way. So that means when I look at my vector equation, it'll look exactly like this, except instead of 0 here, I need that to be 1 minus z, but z for me is u sine v. Does that make more sense? Okay, so this will be 1 minus u sine v, u cosine v, u sine v. May I proceed? How about some partials? What is the partial of r with respect to u? Okay, well, derivative 1 is nothing. Derivative of negative u sine v, that's just a constant. Sine v is a constant, so it's just what? Negative sine v. And then what? Cosine v, and then sine v. Okay, that's my partial with respect to u. Now my partial with respect to v is negative u cosine v. That's derivative here. Derivative of u cosine v with respect to v would be negative u sine v. Derivative of u sine v with respect to v would be u cosine v. Not looking like I'm going to enjoy this, because I'm going to cross those now, right? This equals, oh man, okay, so I want the first component. It's going to be, what? Cosine v times u cosine v. So u cosine squared v minus whatever this is, but there's a negative there, so it'll be plus u sine squared v. Haha, right? That's nice. Okay, then I'm going to do the j component. So I do this one times this one, and then I change the sign. So that's going to be positive u sine v cosine v. And then I'm going to do this one times this one, but subtract it. So is that right? Yeah, this is confusing because you have to do this, but then you have to subtract it, then you have to change sign. So it's really just going to be that, right? So it's minus, is that right? U sine v cosine v? Are they going to just kill each other off? Did I do the wrong one? Sorry, I did. No, that's right. This and this, change the sign. This and this, but minus, then change the sign, yeah. I'm not going to complain if that's the way it works out. We all agree? I put in what? Yes, it's the cross. Right? Cross is a vector. Then magnitude's coming later. Yeah. So now we do the kth component, right? So we cover this up. This times this, negative times negative is positive. So u sine squared v. Yes. And then what? This and this one minus, but then subtract. So it's going to be plus again. I mean, how lucky could we get? All right, that cleans up significantly, doesn't it? This is just what? U, 0, U. U, 0, U. What's the magnitude of this? Square root of u squared plus u squared, which is the square root of 2u squared, which is just root 2u, isn't it? Or u in front of the root 2. Now, I would have to consider possibly absolute value here, but is my u always positive? Yes, my u is always positive. So the square root of u squared should always be positive also. So, all right, I'm good. I'm ready to now come up with my formula, my double integral. So double integral over the surface S of x ds should be equal to the double integral over d of my function evaluated on the surface. So my function evaluated on the surface, my function was x. So all I want is the x component of my surface, which is 1 minus u sine v. I want to multiply that times the magnitude of the cross product of the partials, which was 2, root 2, u, and then dA, so with respect to surface area now, and with respect to area. So let's just distribute that through. Can we put our limits of integration on here? Yeah? Are our limits between constants? Yes, so the order of integration won't matter. So this becomes double integral. I'll go 0 to 2 pi. I'll go 0 to 1. I'm going to have, can I pull the root 2 out of the whole damn thing? Okay with everyone? Root 2 came out. Distributing that u through, I get u minus u squared sine v d, I forget which one was which. It's du dv, right? Du dv. Questions? Mathematica time? I want to get a numerical answer because we're going to find out later that there's going to be a much easier way to do this. But it's kind of like you have to appreciate it first. What did I do? 0 to 2 pi first? 0 to 1? And then it was u minus u squared times sine v d u dv, right? But then I had a root 2 out front. Square root 2 times that. Root 2 pi is what I'm getting. Root 2 pi. Y'all believe it? Can we go with that? Okay, so this comes out to be root 2 times pi. So let's answer the final question, right? Because the question was, find this surface integral, where S is the surface shown below, which was this entire surface. And now what we've done is we've evaluated the surface integral on all 3 surfaces. We're going to add up those answers. So we should just have what? Root 2 pi plus 3 pi over 2? That was it. And then 0 was that other third surface. So therefore, double integral over S of x ds should be equal to 3 pi over 2 plus root 2 pi. Do me a favor, go back to this one right here. This was over S3, right? And we got 0 there. Just change this right here. Oh, change this to S3 right there. That way we know that over S3 it was 0. And then down here, change this one to S2. Because that was over S, wait, was it S2? No, S1. So we went over S2 first. That's what y'all wanted to do. And then we went over S1 or S3, and then we went over S1, and then we add up all the answers, and that's the integral over S. Surface integral over S. Do you see why we took a little time to understand how to define parametric surfaces? Because you need them to be able to do all this. Back to the notes. I was hoping maybe on Wednesday, we all, since it's our last day, we all try and be here on time. Can we go for that? Yeah? All right. By the way, what my plan is to try and finish things out, you know, and we won't really have a whole lot of time to talk about the final, but let's try and talk about the final next time. Like what to expect. What I'll do is I'll pull out the last few semesters' finals, just kind of talk through the things that I tested on. Okay, so we're going to move on now. Oriented surfaces. We need to come up with a couple of definitions and understand some stuff before we can move into trying to do surface integrals where you have a vector field there also. So we have this idea of an oriented surface. An oriented surface is a two-sided surface. I put here just for fun that there are things that are considered to be one-sided surfaces. A Mobius strip, if you've ever heard of a Mobius strip before, that's an example of a one-sided surface. So an oriented surface is a two-sided surface in which the normal vector at every point on the surface exists, and such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations. So let me first talk about the first two conditions. We have to have that at every point on the surface, you have a concept of a normal vector. Remember, like a normal vector for a plane was this vector that was orthogonal to the plane? That was our normal vector. Well, imagine on a surface the concept of a normal vector, meaning that at every point there's like a tangent plane, and there's a normal vector off that tangent plane. So we have to make sure first that our surface, that the normal vector exists at every point on the surface, and then that it varies continuously. In other words, you don't have the normal vector on the surface pointing in this direction, and all of a sudden, instantaneously, going from one point to the next, it switches. Almost like, remember with the derivative, when you had it like an absolute value function, the derivative was positive and then switched automatically to negative. Same thing here. We can't have the normal vector be going and all of a sudden flip directions on us. So it needs to vary. It can change, but continuously, nice and smooth. It makes the transition. So as long as those are held, those two conditions are met, then we can always orient the surface. We can have a positive orientation. So here's a surface, right, a sphere. Positive orientation would be where all the normal vectors are pointing out away from the surface like this. And then normal negative orientation would be where they all point in, right? So we need to make sure we understand that there are now, given a nice surface, there are two possible orientations that we can have for the surface, positive and negative. Now, how do you compute the actual normal vector if you have an oriented surface? So computation is as follows. The normal vector is the cross product of the partials. Does that make sense to you? That's what we talked about last time. The partials give you curves, and then what you're doing is you're taking a tangent vector on each of those curves, and you're coming up with, using those two as vectors on your plane, you're crossing them and getting a normal. We did that last class. But then we're dividing it through by its own length. What does that do? Makes it a unit normal vector, right? It's going to be a vector with length 1, right? So that's how we can compute n. If we needed to compute the actual normal vector, this is the computation of it. And then negative n would be the same normal vector in the opposite direction, right? Just changes the direction of the vector. Now, in the special case where the surface can be expressed as a function of x and y, this right here turns into this. And look back in your notes from last class, we talked about the special case. It just makes it easier if we have that case. Now, closed-oriented surfaces. So what we've been talking about just there was just a surface, right? Did not have to be closed. What does it mean to be closed? If the surface is closed so that it encloses a solid. So the sphere is a closed surface, isn't it? It encloses a ball, like a solid ball. So that solid, E, we'll call it E, then positive orientation is the one in which the normals point away from the solid. So like when we had that sphere, the solid is inside that it encloses. So positive orientation on a sphere, the normals point away from that solid. Anytime you have a solid enclosed, positive orientation is pointing away from the solid. All right? And now we get to the big daddy of chapter 13, and that's this idea of what's called flux. The surface integral of the vector field over a surface. So given a vector field F and an oriented surface S with a unit normal vector n and the vector equation of the surface R of uv with u and v and d, then here's this thing. We'll talk about it. But I want to actually show you what this concept is, all right? The concept of flux. All right, so here we go. We've got this sphere, right? We have a vector field. This is going to slow. I don't have the entire vector field here. No, I do not have the entire vector field. I apologize. I don't. But remember, in this three-dimensional space, let's say we've now defined capital F, a vector field. So at every point, there's a vector, right? Every point. So if I look at this sphere surface, right, as a surface, and let's just focus on this red patch, which we've done in the past, I'm first going to show you some normal vectors on that. So those are normal vectors. What does it mean that those are normal vectors? At the four corners of this patch, I'm computing a vector that is like tangent to the, well, there's a tangent plane at each of those points, and I'm showing you the normal vectors off those tangent planes. Yes? And their unit length? Okay. Now, let me show you the vector field at each of those points. Now, the vector field does not have to point in the same direction as the normal, does it? Right? It does not? It can just be whatever the vector field is. So we have a green vector, which is showing you like a direction of flow. Then you have a normal vector, which is like that normal off the plane that's tangent. Yes? All right. Now, let me show you the flux. Try and... it's hard to see it. It's the black vector, all right? So what is the flux? Well, let's go up to this computation. What is it? It is the vector field, right? Dotted with what? The normal vector. It's the vector field dotted with the normal vector. Do you all see this? Now, how about this right here? That's the same thing, right? Because our normal vector. This is like our normal vector, but it hasn't been scaled, right? It's not divided by the magnitude of the normal vector. What does that represent? What am I measuring here? What does the dot product give us? You know what? This might help us right here. I think this one might do it. And that other one in the background is getting in the way. Okay, maybe I can do it this way. Look. I'll try and draw this. Okay. That's F at that particular point, right? The normal vector is the red one, isn't it? That's this one right here. Okay? Can you tell what the black vector is there? It's the projection of the field F onto the normal vector. It is the projection down onto this. You see that? What you're doing is you're saying at this point, the field is trying to push you in that direction, right? But if you take that and you project that vector down, you're looking at the component of that vector that's pointed in the same direction as the normal vector. So going in the direction green is like equivalent to going in this direction parallel to the normal vector with that magnitude. And so what you're doing is somehow measuring a flow out of that point. And then what you're doing is you're doing it at every point. And so you're getting like this total flow out of the surface. So if the vector field represents like a magnetic force or fluid that's moving, then it gives you like if the surface was like they compare it to like a fishing net. Okay, if the surface was a fishing net and then there's water flowing out through this net, you're measuring the total flow out of the total surface. Got it? Now there might be some flow in and some flow out, but you're getting a total flow, which is called flux. Understand? That's geometrically what's happening. Here are the formulas we'll be using for it, though. Let me see if I added anything else in here. Oh, some other things on notation. Notice that it's a double integral over a surface. Again, that's the same as what we did before. But instead of a scalar function, we now have a vector field, right? Instead of d capital S, we have d capital S vector. All right? What does this mean? What does d capital S vector capital S mean? It means the normal vector times ds, where ds was our normal differential of surface area from the previous type integral. And what does ds by itself mean? I'll write it down on the board. Let's see, F, I want to write this so you can see it here. ds. Okay, now this is the same as F dot NDS, which is the same as F dot, what do we have? RU cross RV DS. DA, sorry, DA. And this is over D now. Well, I'm not going to write what the integrals are integrating over because they're up here. What I'm trying to get you to see is what the relationships are between these D things. So according to this, ds would be the same as nds, right? Those are the same? Trying to find a decent marker. Hold on. What was n, though? I put it on the board just a second ago. What was n? It was RU cross RV over what? Magnitude RU cross RV, right? ds, right? These are the same. And somehow that's equivalent to this. Agreed? Which would imply what? That dA, what's dA? Yeah, what did we say it was? I mean, look at this. If this turns into this, right, then what went away? That's right. So this would have to be, dA would have to be magnitude of this, right? Or I should say it this way. ds would have to be this. Can I write it that way instead? So look, if I replace ds with magnitude of the cross product dA right here, then they cancel out and then you get this, right? Okay, this is going to be tricky, all right, because we are going to use different versions of this formula. It's going to depend on the problem. What I want you to see in this one is for the middle integral, all right? For the middle integral, what we would need to know is we would need to know what the normal vector of the surface looked like, okay? And we would be integrating with respect to the surface itself. Where here, we would need to know, this is kind of like the normal again, right? But it's just a cross product. And we would just need to be integrating with respect to area over D. See, there are two different things here. It's hard for me to explain how we're going to use which one early, but I want you to pay attention to it. Sometimes this version is going to be easier to do than this version and vice versa. All right? So let's just get to trying to do an example here. Find the flux of the vector field F across the unit sphere. So we have a unit sphere, we got our surface, we've got our definition of our flux vector field. Let's go for it. What is the parametric vector form of the sphere? And it's a unit sphere. What's the parametric? So unit sphere. Okay, so we used R view V is which one did we use? Sine U cosine V, then sine U sine V cosine U. And the U was like the phi, right? So U went between 0 and pi, and V is between 0 and 2 pi. Are you looking in your notes to get that? Yes, okay, good, because I've done this in a different class before where we interchanged the V and the U. Like we just rewrote it different way, where we did sine V, cosine U, sine V, sine U, cosine V, and then just switch these around. And so I just want to make sure I'm going off of what I did in this class, yes? Okay, so we already did all this cross product stuff already, right? We did before? Okay, so let me ask you this question real quick. Looking at this formula for flux again, we're going to need to do basically one of these two. All right? This just tells you what you need to do. Okay, that's the definition of the flux integral right there on the left. Well, I need to either compute this or this. Now, when the second one is valuable, the middle one here, is when the normal vector of your surface remains constant throughout the entire surface. Like if you're on a flat plane, right? Like let's say the XY plane, your normal vector is always the same, isn't it? Or even on a plane that has an angle, isn't your normal vector always pointed in the same direction? Understand? So this becomes valuable if that normal never changes. But if it does change, you've got to go with this one. So we're going to go with that third part of this, right? The last part of that equation there. So I want to know this, which is really just the double integral, right, over D of what? F dot RU cross RV. So F dot RU cross RV dA. What do you think I mean by F? the vector field, but my vector field was what in this problem? It was YZX, wasn't it? I can't plug YZX in here because I can plug in YZX as a vector, but do you remember before when we had F here, we meant scalar F, we meant evaluate scalar F at the vector on the surface? Same thing here. I want to evaluate this vector field on my surface. So Y is going to be replaced with what? Sine U sine V. Z is going to be replaced with cosine U. And then X is going to be replaced with sine U cosine V. Got it? But it will be a vector instead of a scalar function from before, which is why it's so important to have a dot product, because this is a vector also. So we got two vectors, we're gonna dot them. With me? All right. This is double integral over D of F, this part right here. Evaluate the vector field, so that's going to be Y, so sine U sine V, Z, which is cosine U, and then sine U cosine V. I want to dot that, right? Dot that with this part here. Now we've crossed RU, partial of R with respect to U and V, like twice before, I think, in this class, right? And when we crossed them, we got, do y'all remember? I have it right here, but it would be like, I think it's sine squared U cosine V, sine squared U sine V, sine U cosine U, sine U cosine U, and then dA. I just want to check back in the notes that that was in our notes. It's there? I believe you. I want to see that I did it. Oh, here we go. Hold on. Was that it right there? No, see, here was the magnitude. We did it before that. We must have done it maybe the day before this. Oh, here we go. Here we go. No. No, see, we did it specifically for that case. Maybe we never did. Oh, there it is. There. Okay, here we go. So we did it on day 25. We did the cross. So we took the partials of the sphere, and then we crossed them, and we got this. Okay, and then we found the magnitude, so that's more than what we need here. We just did that cross. Okay, so notice we don't need the magnitude, which is good. Okay, so we are taking that. Now, remember how to do dot product, right? Dot product is going to be, first component times first component plus second times second plus third times third. So this will give us double integral over D of, I'm getting sine cubed U, sine V cosine V, plus sine squared U cosine U sine V, plus sine squared U cosine V, dA. And now you'd go and change your limits of integration. So U and V were the variables, right? U is between 0 pi. V is between 0, 2 pi. And then all that stuff again, right? I'm not going to rewrite it. dV du in this case. All that would go right there. And that would be it. Then you'd have to evaluate that. So you'd integrate with respect to V first. So this with respect to V would be pretty clean. This with respect to V would be very clean. This with respect to V would be very clean. You get that answer. You plug in 0. You plug in 2 pi. Whatever happens, happens. Then you do it again. You integrate with respect to U. That would be a little uglier, but it would work. Oh, no, those are pretty simple. This one requires a little bit of work. Sine cubed U, right? Peel off 2 factors of sine, turn it into 1 minus cosine squared. And do we care to know an answer? No. No, we'll move on. Whatever that answer is, it's a measurement of the flux. That's the flux. All right? Okay, now some very special cases of flux, of evaluating the flux. Anytime your surface can be written as a function of 2 of the variables, the computation of flux becomes much easier, because you don't have to look at this cross product, this F dotting with cross product the way we do when it's not a function of just 2 variables. So what we have here are going to be 3 different cases, and I believe in your notes this may be incorrect, so you might have to adjust some things here. Let's just start with this though. Okay, if your surface Z can be expressed in terms of X and Y. So that's our first surface we ever talked about in this class. X and Y are our domain. The ground is our domain. Our surface lives up here, right? If that's the case, then, and you look at your vector function, or your vector field F in its component form, PQR, then when you do this cross product, it will become much nicer. And you can go back, and we did it last class. I showed you in this special case what happens when you take this cross product. Do you all remember last class? It was a whole like Thanksgiving ago. In the special case, this was it right here. When you did the partial cross product, if U and V were used to determine your Z, in other words, Z was a function of, we could say, X and Y, then it just turned out to be this vector. Negative partial Z with respect to U, or if you want to say with respect to X, negative Z with respect to Y, we could say, instead of V, and then a 1 here. If you take this and you dot it, right? If you dot this thing with F, then what you get is this. Does this make sense? Negative P, okay, negative comes from, it was negative, wasn't it? And it was partial of G with respect to X. That was our partial of Z with respect to U. Okay, and then you have the next part of the dot would be the middle, the components. So that would be your Q times the negative Z with respect to V, which is this. Partial G with respect to Y. Do y'all get that or not? And then the last component was 1. 1 times R would give us this. So it becomes much easier because look, if you know the surface, you know the vector field, all you have to do is compute that right there and then integrate over D. And you're done. What's D? D is the domain of the surface. So it's a domain that we've done in the past. We'll do an example, all right? Now, what if instead not Z is a function of X and Y, but your surface is sideways? So, you know, X, which is this direction in the room, right? Out this way. X is a function of the Y in the Z variable. So your surface is like sideways, like this. If that's the case, if your vector field's PQR, then it turns into this instead. Now I won't go through showing why the signs are the way they are, but you could verify it yourself. In fact, the book asks you in an exercise, I don't ask you to do this for homework, but the book does ask in an exercise to show that it's true, that this is the formula for it. So who still has the typed out notes? Did you print those out? Did I have this correct? Was it P negative Q negative R for the second one? Okay. It might be the third one that's off. And for the third one, if y is a function of x and z, then, and of course f is the same, then it becomes negative P, positive Q, negative R. Is that what you have there? The signs are off, right? Okay, so make sure you fix it there. Anyone else who has been printing off the notes online? This is correct. What's there is incorrect. So this one, y is a function of x and z, so our surface would be like coming out this way, right? From the xz plane, so it's out like this somewhere. Oh, I also say another way you can remember this is that your normals, if your surface is like the traditional surface like this, all your normal vectors would be pointing up, wouldn't they? In some respect, where pointing up out the z-axis. So I'm saying up this direction, parallel to the z-axis. If your surface x is a function of y and z, then it'll be pointing out this way towards the reader, towards out the x-axis. And then, of course, if it's the y is a function of x and z, then it's pointing out this direction, the normal vectors on the surface. That kind of helps you dictate which of those you can use. Okay. Find the flux of the vector field. Here's our vector field. It's the vector field xy, yz, zx, where s is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the region x between 0, 1, y between 0, 1. Use upward orientation. See, for flux, you have to have an orientation. Because you want to know if you want to consider your normals pointing out in this direction or the normals that go in. And so when I say use upward orientation, I mean on this picture, I want you to use the normal vectors that are pointed up. All right? Down is obviously this way. Now this is a function, right? Z is a function of two variables, yes? Isn't it? So I could say z is g of xy. So this is a special case. F is given to me by that vector field. And then my domain is actually given to me explicitly here. I want to integrate over a rectangle, don't I? Or a square. Let's see if we can set this up. So I'm trying to find the flux. My vector field was, help me out because I don't have my notes with me. XY, YZ, ZX, and then Z was 4 minus X squared, Y squared. Okay. So I'm going to start this out by noticing, hey, special case, right? Special case where Z is a function of X and Y, right? I'm also told that my normals need to be pointing up, which up means up the z-axis. And the special formula that I just had said that I can use this, right, as long as my normals are pointing up the z-axis. Now, had I been told in the problem to use negative orientation, right, then I would have needed to be looking at the normals pointing downward, right, which means guess what would happen here? Change the signs of everything, all right? I would change signs because my normal vector would be, instead of n, it would be negative n. So all I would do is change signs, but I need to pay attention to that. All right, well, what's the formula say? The flux integral, right, is going to turn out to be this. So negative p partial g with respect to x, put that over here. So my flux integral will be double integral over d of negative p. What's negative p for me? Negative xy. Okay, times, what is, see, notice I'm not changing anything to u and v because it's a special case, right? So that's, this was up here, p, q, and r. So there's my negative p, right, negative p. Now I need partial g with respect to x. What's partial g with respect to x? Negative 2x. Okay, minus q minus yz, partial of g with respect to y now? It's partial g with respect to y. Negative 2y. And then plus r. What's r? Zx. This okay? All of that dA. Now, what is my domain? It's my restrictions on what two things? X and Y, right? And I was given that in the problem, right? So I was given that X and Y were both between 0 and 1, so it doesn't matter which one I do first here. And now I have negative xy. Let me clean that up. That's what? 2x squared y plus 2y squared z plus 2x dx dy. Sorry? Where am I missing what? 2x should, this last one? Oh, I missed the whole z up here. Oops, why, yeah. Oh, that's a z, it's not a 2. Wow, that's why I strike my z so I don't confuse that, and I confused it. That's the first time in many, many years I've done that. This is zx. Okay, now we're good? Okay, what's wrong with this? That's right. See, these are integrals involving x and y. You still have a variable in there. It's not a constant. It's z, right? It depends on x and y. You need to not have z's in here. But z is a function of x and y. It's exactly 4 minus x squared minus y squared. So all I need to do is, wherever I see a z, I need to replace it with this. And then I can go about doing my integration. So this will become integral 0 to 1, integral 0 to 1, 2x squared y plus 2y squared z, but z was 4 minus x squared minus y squared. And then plus, again, z, 4 minus x squared minus y squared, x, dx dy, or dy dx. And we could, clean this all up, couldn't we? We can multiply all this through, distribute all that through, collect like terms if there are any, and then we could, it's all polynomials in x and y. We could integrate pretty easily, and we'd be done, right? Okay. Now, a natural question arises, did you have to use the special case? Could you have done it just using the formula? Well, if I would have used the formula, without the special case formula, if I would have just gone with the straight flux, the way it's defined, I gave you the equivalent ones, right, over here like this. I said, which of these would we use? The first thing I would ask myself, is the normal vector always the same? And on this surface, it changes, doesn't it? It changes the direction. So I wouldn't use the middle one. I'd use that one on the end. So I'd need to be able to figure out what r is. But r would be easy, because r would be, I'm just showing you that you could have done it this way. You would have just let x be u, let y be v, and then let this be 4 minus u squared minus v squared. That's your vector. That's your parametric surface right here, right, in vector form. It's like xy, 4 minus x squared minus y squared. And then you'd find your partial, right? What's your partial with respect to u? 1, 0, negative 2u. Partial with respect to v would be 0, 1, negative 2v. Then you could cross them, right? Understand? I mean, we could do the same exact thing and just use that outside formula. You would have to replace your f, right? You have to plug in for x, y, and z. You'd have to plug in these into your vector field. I'm not going to do the rest, but do you all understand what I'm saying? That you do not have to use the special form, but it will take you longer because you actually physically have to go cross those. Then you have to dot it with the f. You have to replace the x, y, and z in f with this stuff. Just takes a little bit. Yes? Nope. Nope, because you're not changing variables. You're starting the original problem, defining your surface this way. This draws the same surface as that one up there. So we're not converting from one coordinate system to another. We're just really calling our variable something else, and we're drawing it using something else. Right? We're drawing it using a parametric form like vectors, drawing the surface with vectors, instead of drawing it like a traditional surface when we first started learning about functions of two variables. Okay, let's see where else we can go with this today. Find the flux of the vector field F equals 0y negative z across the surface S, where S is the part of the paraboloid y equals x squared plus z squared, with y between 0 and 1, and the disk x squared plus y squared equals less than or equal to 1 with y equals 1. Use positive orientation. Okay, the picture helps, okay? We have a paraboloid, which is like a bowl, right? This paraboloid is opening out which axis? The y-axis, right? So it's coming out the y-axis, like a bowl. Then we have this disk, x squared plus y squared, x squared plus z squared less than or equal to 1, means everything between, like every circle that creates that entire disk, but our y value is stuck at 1. So that means move out on the y-axis 1, then draw every circle possible with radiuses all the way from 1 down to nothing, right? All the way 1 to 0. So I guess the first question would be, could you visualize this with just this information? That would be the first thing you have to do. Positive orientation. What does positive orientation mean for us here? Outward, right? Outward from the solid, because it encloses a solid, right? So positive orientation means outward. So on this disk, positive orientation means it's going to be going down, like pointed down the y-axis, right? Where on the other one, the paraboloid, which way are those pointed? Well, it'll depend on where you are, right, on it. But tell me about what component is always, like in terms of the y-axis, this is pointed always in the negative y direction. Would you agree with that? I mean, the paraboloid is coming out from this wall, right? Like it's coming out like this. So if do y'all see it or not? If I put the normal vector anywhere, no matter where it is, do you agree that the y component is always negative? The y component. The part of it that's pointing that way is always negative. Yes? Okay. All right, so let's just keep all that in mind. See where I'm going to go here with this. We're going to integrate over both surfaces, right? Okay, let's try this. So I'm not going to rewrite all the information. I'm just going to try and draw a picture, though. We'll call this front side S1. We'll call this back side S2. We want to do double integral over S of f dot ds, which should be the double integral over S of S1 dot ds plus the double integral of S2 f dot ds. Right, so we're going to do both of those, right? Positive orientation, though, we will need to consider that. Trying to look here. How much time do we have? 17. All right, let's do it. Let's do S1 first. Tell me about S1, everyone. Let's practice first. Can you give me the vector form of that surface of S1? What's going to be 0? S1 is this disk, right? Right. So what was that? Where was that disk? Which is this face here? The y coordinate was 1, right? That's always 1. And then the rest of it was just I need to draw all the circles, right? Okay, so let's try it again. This would be 1 in the middle. And then what here? U cosine V would work. U sine V? Yes? By the way, let me just jot down the vector field up here. What was the vector field? Was it was 0, y negative z? Right? That was our vector field? Okay. So I want to show you 2 ways of doing this, okay? 2 different ways. There's actually 3 different ways we could do it. Let me ask you this, though. If this is our surface, can we look at it as one of the special cases? We could? What's that? Yeah, because it's a circle this way, y is a function of x and z, yes? So we could look at it as a special case. We could also not give a damn and just do this, right? So let me see, I've got 20 minutes. I want to show you just this one surface. I want to show it to you 3 different ways so that you can see that it's not just a blind swing at it. You actually want to think through it a little bit before you do it. Because one way is going to be easier than the other, and one way is going to be real easy. Okay? So let's start with this. I'm going to start with S1. I think we'll only be able to do S1 today, and we'll come back and do S2. How about we do the traditional formula, which is just one of those 2 down there? I'll do the one at the end. So I need to know what RU is, R partial R with respect to U. What's that? Cosine V, 0, sine V. Okay, what is partial R with respect to V? Negative U sine V, 0, U cosine V. Cross them. I'm going quick. 0, right? Now when we cover up the middle, go here, I get what? U cosine V squared. Then I come this way and I get minus, but then minus, so it'll be plus U sine V squared. That's just going to be U, right? And then over here, we're going to get, last one, 0, 0. So we get 0. Yes? I'm going quick, but do you agree? Do you know what I'm doing? Yes? Okay, so now what I'd like to do is for the flux, I'm going to do the double integral over D, which is the domain of my parametric surface, of the F dotted with the cross product. So what's my F? What's my F? 0, y, but what y am I going to use? I mean, 1, right? It's the y of this. It's not y, it's the y of the surface. So it's 1, and then, what is it, negative z? Negative z for me is going to be u sine v, right? That's it. Now dot that with what? 0u0, which dA, which when you dot that, what do you get? Double integral over d of u dA, right? That's it. And then what's my restriction on u and v here? 0 to, well, they're both constants, right? 0 to 1, 0 to pi of u, and now this one does matter, right? d v du, if I'm going to do it that way, right? Because u is my radius, right? So u goes from 0 to 1, v goes 0 to pi. So integrate that real quick. Antiderivative of u with respect to v would be uv. Evaluating that from v equals 0 to v equals 2 pi, which is just 2 pi u. So this is going to be integral from 0 to 1 of 2 pi u du. What's the antiderivative of 2 pi u? Pi u squared, evaluated from 0 to 1, which is pi. Okay, the flux out that surface is pi. Got it? That's one way to do it. Now, let me do a different approach. Different approach is to look at it as a special case. If it's a special case, S1 special case, where I can say that x is a function. Do I use g in those notes, or do I use something else? I use g, yes. So I'm saying x is a function of y and z, right? So x is a function of y and z. Specifically, x is what? Wait, was it x? Sorry, it wasn't x, it was y. Cancel. Y is a function of what? X and z. I apologize. I'm looking at this one right here. Y is a function of x and z. So since it's a function of x and z, I just need to be able to compute this right here. All right? So what is my y as a function of x and z? What is it? What is g of x, z? It's constant. It's the constant 1, right? It's a constant 1. That's what my y is always. Okay. And what's my f? My f was 0, y, negative z. Are y'all following this or not? Okay, and this is my PQR. So what it says, the special case says that the flux will be equal to the double integral over what? D, which is the domain of my region of integration, right? I mean, this is my region of integration, the domain of the function. We'll talk about that in a second. But then it's all this stuff, right? It's negative p, so for us that's what? Negative 0, right? Which is 0. So I'll put it in here. It's negative 0. What was the partial of g with respect to x? Doesn't matter, it's constant, right? 0? Do you agree? Plus, now the next part, was it plus? Q, right? Q, what's Q? Q is y, right? And then the next part, negative r, which for us is negative negative z, so positive z. But then what's partial to z with g with respect to z? 0. So I believe this would have been plus z times 0. d a. Everybody okay with that? Yes? This is equal to, no one has a question right now. We're okay? That's this? Yeah? What's y? It's always 1, isn't it, on the surface? So isn't this just a double integral of 1 dA? And what's the double integral of 1 with respect to area over this d? What is that special case of? I mean, that's just the what of what there. That's just the area of the region of integration. What's our region of integration? This is the kicker right here. What's the region of integration in this problem? So remember, this was we were doing this disk, right? But we were looking at it as a surface, right? So the domain of this is actually the projection of that circle down to the xz plane. What is that? It's a circle on the xz plane, right? What is its radius? You see? That's the domain on the ground, isn't it? But the ground is actually the wall. That domain is a circle, right? So you'd be thinking like going to polar here. You don't need to go to polar because our integral turned out so nice, it's just the area of that region. So pi r squared, but what's the radius? 1. So this is just the area of D, which equals pi. Same answer. Yeah? So of those two that I showed you, what do you think? Second one? And now I give you the third one. All right? And I know you might be saying, look, okay, two's good enough. Don't confuse me. All right, so let me look at S1 again. And what I want you to notice is that because S1 is a plane, right? It's a circle, right? It's a disk. But it's like a plane, isn't it? Y equals 1. What can you tell me about the normal vector on that plane? It's always the same. What is it? What is the normal vector? It points straight that way. What's the vector that points straight that way? 0, 1, 0, right? That's the normal vector. How long is that vector? What's its length? 1. So that is a unit normal vector, isn't it? And according to this, I can just do F dotted with that normal and integrate with respect to surface area of S. Okay? So check this shit out. This is the same as doing the double integral over S, not D, of F dotted with the normal vector ds. See, that's different than the dA one, right? I'm still going to be stuck with the surface integral when I'm done here, but watch how nice things become. What is F for us here? What is it? 0, negative y, z, right? Dot that with 0, 1, 0, right? And what do you get when you dot those? You get y again, right? You get y again? Okay, so let me go to the next page. This is the double integral over S of y ds. But again, what was y? 1, because we're still on that disk, right? So this is just the double integral over S of 1 ds. This is not the area of the projection of the shadow onto the ground. This is actually the area of what? Of the surface S. So you better know the area of this surface or else you're in trouble. Or you better be able to compute the area somehow mechanically. But this was a disk, right? The disk was our surface, and that disk is right? It's just a circle. We know the area of that circle. What is it? Pi r squared, right? Which for us is just pi. So this is just pi. Almost no work at all, right? But do you understand the difference between this and, whoa, I passed it up, and this? This was the area of the D, which was the domain area, as opposed to this one, which required us to know the area of the surface. If you don't know the area of that surface, you're in trouble at that point. You'd have to somehow find a parametric representation of that surface and do all the work for it, and it would be hard. But if it's a disk, then you would go after it this way. So now, in retrospect, looking back at the problem, when I'm sitting here and I'm saying, okay, I want to compute the flux over that disk, the first thing that pops out of me is all the normals are the same. The normals are the same. If the normals are always the same, can I find the area of the surface? Yes, because it's a circle, pi r squared. I'm going to know that. I go with that third option. It's the quickest, easiest way to go. Do you understand that? Now, on the other side, the backside, the paraboloid, which we'll do next class, we do not have a constant normal, do we? So it's not going to benefit us to try and get that normal like it did in that last one, right? On top of it, let's say even that it was a constant normal. Do you know the surface area of the paraboloid? No. So you still would be in trouble. So I'm thinking special case on that one, because special case, it is a function, right? It is a function of x and z. And so I can do that special case. I just have to take into consideration the orientation, right? I'd need to get that answer and then multiply by -1 to switch the orientation out. Okay, wow, we're still in 13.7. We still have another flux one to do. Let's look at this one right here. See, we won't do any more, but let's talk about this, because I don't know if we really need to do these or not. We have 4 surfaces, right? How would you do this front face? Is that a what? It's flat, yes. It's flat. The normal vector, right? The normal vector is always going to be what here? What vector is it? If this is the x-axis, it's just going to be 1, 0, 0, right? And then if you're going to do that, hopefully what will happen is at some point you'll need to know the surface area of this, right? Do you know the surface area of this? Yes, it looks like half circle, right? And then same thing with the back one. Would work possibly the same way. What about the bottom one? It's a rectangle or perhaps a square here. You know all the normal vectors there, right? Yeah? And then what about the cylinder? No, this paraboloid looking thing, parabola looking thing. Or, well, is it a cylinder? Yeah, it is a cylinder, sorry. So that's cylindrical here. That one you can't avoid it. You're going to have to use probably a special case there, because the z coordinate of the cylinder is a function of x and y. So you just do that special case. I believe that's the last example there. I'm not doing any more problems, and I told you we could get out of here, but I kind of lied. I want you to just see where we're going. What's Stokes' theorem? 9 integrals over vector fields. That's not it. Damn it, I don't have divergence theorem. I don't have it up here. Well, we're going to find out, though, the big result of this chapter, 13.9. I'll jot it down because we will have very limited time next class to talk about this, because we only meet one more time. Please hold back the tears. Here's what it says. I just want to make sure I write, yeah. That's the big result right there. It says basically that the flux that we're trying to do right now, right, can be done by just doing a triple integral over the solid that's enclosed by the surfaces of the div of f, dv, which means that this problem that I just showed you right here can be done so much easier after you have the divergence theorem, because this encloses a solid, doesn't it? And this is saying that that surface integral that you're trying to do, the flux, instead of breaking it up over all those four surfaces, all you're going to need to do is figure out what the div of f is. And div of f is super easy. It's partial, partial, partial added together. And then you just need to be able to integrate over that solid triple integral, which means you need to somehow give me a way of defining that solid. Which this is just, and it's a pretty easy solid to describe, right? Your x and y are between two constants. Your z is between function 0 and then the cylinder. So it would be like from, I can't tell what the limits are here, but looks like x goes from -1 to 1. Your y goes, or no, x goes from 0 to 2, y goes from -1 to 1, and then your z would go from 0 to whatever the top is, which is square root of 1 minus y squared. Then whatever the div is, in other words, it's going to be freaking easy. We're not going to have to break it up into 4 separate surface integrals to do it. It's a beautiful result. All right, now I'm out of time, so I've yapped enough. Homework? Do y'all want to talk about homework yet? No? No homework? You should try doing a couple of problems out of this section, 13.7. Page 816. 5, 7, 17, 21, 20. Okay, so these that I circle here, those are flux. So you may not be quite ready for that, but you can try. These are just surface over scalar f. So those are scalar, surface integrals over scalar functions. These are flux, so you have vector fields. All right. Wednesday, we'll try and finish up Stokes' theorem, divergence theorem, do the best we can. Talk about the final. Our final's on Monday. So it'll be from, what, 11 to 1:45? A week from today.